Hello. So today we'll just be talking about one theorem known as the power of a point theorem. So let's get a circle, um, and let's give us a point, draw a bit better, a point P. And now this line crosses a line through P that crosses the circle 2 times and intersects one at A and once at B. And let's label it A1, B1. Now let's say we draw another line. Let's label this A2, this one B2. Now basically what the power of the point theorem says that for any point P and a line through P which intersects the circle points A and B, PA times PB is always the same. That means this length times this length is equal to this length times this length. And this will always be true for any point P. It doesn't even have to be outside the circle. If there's some point P here, and you cross the circle twice like this, A, B, and A1, B1, I guess, and A2, B2, the ratio, well, not really the ratio, but P to A1, this length times this length, will still be equal to this length times this length. And even if P is on the circle itself, though in this case it might be a bit more difficult to figure out which one's A and which one's B. Also, another interesting property is with tangent lines. So if you have some point P here, and this going through A, this one going through B, even though it really only intersects the circle at one point, it's not really doing that. What it's doing is you can think of it as intersecting the circle twice at this one point. So PA times PA, so PA squared, would be equal to PB squared, which means that if this is a tangent, that means these two lengths have to be the same. And incidentally, this could also be used to prove that a line is tangent to a circle if you have another tangent line lying around somewhere. And if you have like a tangent line and another secant line like this, let's just call it CD, you know that PA squared is equal to PC PD. And honestly, like, there's a lot of applications for the power of the point theorem, even though it may seem a bit obscure. The conditions aren't that complicated. All you need is a circle, some point P lying anywhere inside the circle, outside the circle, either works, and a line going through P that intersects the 2 points. Though I will say this, that normally you need at least 2 lines originating from P for this theorem to be of any use. So just as a sort of proof for this, let's give you a circle. Let's give you a point A here, a secant line through here. Should draw that a bit better. Secant line through here, and also let's also draw a line here and a line here. And I'll just label these A, B, C, D, and E. I'll also draw 2 lines here. Now, what we're trying to prove is that AD times AC is equal to AB squared, and that's just saying that this secant line is here, this length times this length is equal to this length squared. Now if we rearrange this, this turns into AD over AB equals AB over AC. And let's look at what these lines are. AD and AB. And we also have AB and AC. Now, if you think about it a bit, since they share an angle here, that means what we're really saying is that triangle ABC is similar to triangle ADB. Now, since we've already established that this angle here is the same, that means to prove that it's similar, we need to prove that this angle is also equal to this angle. So to do that, first let's go with angle BCD. Now, since this is an inscribed angle within a circle, angle BCD is equal to the length of BD divided by 2, assuming that this angle is in radians. So arc BD here divided by 2. Now for angle ABD, since ABD is the angle between a tangent line here and a chord here, its measure is actually also equal to the length of BD over 2, assuming of course it's in radians. Now, right now we've proved that these two triangles, ABC and ADB, they share two angles, which means that they are similar triangles. And since they're similar triangles, this relationship holds, which can be turned back into this, which in a way proves the power of the point theorem for basically any point P outside the circle. And we proved this using a tangent line and a secant line, but you can really do this with any combination of tangent lines and secant lines as long as the point is outside the circle. Now for the second part of the proof, we need to prove that this also works when it's inside the circle. Let's get a point P here. This is in the center, just some random point. Let's get 2 crosses here. Let's connect these lines, and I'll just name these. How about A, B, C, and D? So what we need to prove is PA, PD is equal to PB, PC. And we can once again rearrange this. So it's PA over PB is equal to PC over PD. So once again, this is another sort of similar triangle problem, so you have to prove that these two triangles are similar. So first, we have one angle already. These are vertical angles, which means that they have to be equal. Now, since this angle and this angle, since both of these angles subtend the same arc, this arc here, that means that they are actually also equal. So basically at this point you have 2 angles that you know to be equal, and then you can easily prove that these third angles are also equal in measure. So by this point, basically you've proved that these two are similar triangles, which means this relation holds, which means that the power of the point theorem holds for all points inside the circle. Now, I guess I'll just leave you with one question. So, there's a triangle with side lengths 20, 21, and 29. And let's just draw this. This is not to scale, by the way. And there's an inscribed circle inside this triangle. So the question is, find the area of the circle. Anyways, have fun and see you next week.